All right, this is Professor Pelton. This is part 2 of Chapter 3, Section 1. Okay, so if I have um, tables of coordinates, I can figure out whether the relation is a function or not. I can make a mapping if I need to, or I can just look at them. It depends what I'm going to do. So I'll make a mapping. So input, output. So I have 1, 2, 3, 4 in my input mapping. And my output, I have 6, 8, and 9. So 1 goes to 6, 2 goes to 6, 3 goes to 8, and 4 goes to 9. So every input only has one output. So this is in fact a function. Right, that works. Okay, so the following, we'll do an input and output. So we'll make this relation into a mapping. So 6, 8, and 9, and then 1, 2, 3, and 4. So 6 goes to 1, 6 goes to 2, 8 goes to 3, 9 goes to 4. So the problem here is that 6 goes to two different numbers, so one input has two different outputs. So this is not a function. It's still a relation, because a relation is just a mapping inputs to outputs, but that does not mean necessarily it's a function. Okay, all right, pause the video, try the student problems for yourself. Okay, so we'll try the next one. Input, output. So I have 1, 2, 3, 5, 1, I'm sorry, 1, 3, 5, and 2, 4, 6, 8, 2, 4, 6, 8. So 1 maps to 2, 3 maps to 4, 5 maps to 6, and 5 maps to 8. So 5 goes to two different values. So that is not a function, because we have an input that has multiple outputs. That's not true. That can't happen. So it's just a relation. So input to output. So we're going to have 1, 3, 6, 8. 1, 3, 6, 8 is my inputs. And then 2, 4, 5. 2, 4, and 5 are my outputs. So 1 maps to 2, 3 maps to 4, 6 maps to 5, and 8 maps to 5. So everything maps to a singular output. So this is a function. Okay, and these are all finite cases or discrete cases. We can have infinite cases too, which we'll go over later on. Okay, so it'll be equations and you have infinite inputs and outputs. So you can have implicit form and explicit form, okay, of equations, which you can make tables of values that are infinite. Okay, so implicit form is an equation that has not been solved by an isolating single variable. There's no real distinction between the independent and dependent variable in this form. An equation that has been solved and isolated in terms of an independent variable. So we'll take this one right here, and we'll take x squared plus 2y equals 1. So we're going to make this in explicit form. So I'm going to minus x squared. So what I get is 2y equals 1 minus x squared. Then I'll divide by 2. So y equals 1/2 minus x squared over 2. So that is in explicit form. So if you're in computer science, or if you just want to make things into functions and put an output, you want it in explicit form. So you put one input, you get one output essentially. All right, so these are the continuous examples, because you can put in any decimal you want for x and get in out y's. Okay, so the question is, are these in fact functions? That's the question. Let's get rid of this mistake x here. What's up with that? We'll fix that. Okay. All right, so the question is, are these actually functions or not, or just relations? So can I solve for y? So I'm going to minus x squared. So I get y equals 4 minus x squared. All right. Determine whether each relation represents a function. Let's determine whether the equation can be defined as y as a function of x. Okay, so this is f of x equals 4 minus x squared in function notation. So this is a function. Okay. It's also a relation, right? Everything's a relation, but it's also a function. So if I do this one, I'm going to minus x squared. I get y squared equals 4 minus x squared. Then I have to square root, so I have to square root the y, and I have to square root this. So in fact, I get y equals plus or minus the square root of 4 minus x squared. So the problem is if I plug in an x value now, I'm going to get two y values because it's a plus or minus. This is not a function. It's in fact a relation only. Okay. All right, pause the video, try the student problems for yourself. Okay, so if I minus 2x here, I'm going to get y equals 6 minus 2x. So that can be written in a function notation, so 6 minus 2x. So this is a function. Okay, so for every x I plug in, I get a 1 y value. However, if I try this one, I'm going to get y squared equals 1 minus x squared. And if I square root, I'm going to get y equals plus or minus the square root of 1 minus x squared, which for every x I plug in, I'm going to get two y's, right? That's a problem. You can't have two outputs for every input. So this is not a function. It's in fact a relation. So if you try to plug these into calculators, or graphing calculators, into the function graphs, they won't work. You can plug them into relation graphs, which are different, but not function graphs. Okay, so independent versus dependent variable tends to be the question. So the independent's the one you plug in because you can plug in anything you want, and the output variable is the dependent variable because whatever you plug in is going to give you something, and that what that gives you is dependent on what you plugged in. That's why it's called the dependent variable. So if I have this implicit form of the equation, which is the area of a circle, if I solve it, okay, I get a minus pi r squared equals 0. So a equals pi r squared if I add pi r squared to the other side, correct? That is the explicit form. So I can write down in function notation. So a of r, right? A of r, that's not a very good r. Let me try that again. There we go. A of r equals pi r squared is the function form, which you'd use in like Microsoft Excel or your calculator. All right, so the independent variables are, so you plug in an r, it will give you an a, which is the dependent variable. So the area is dependent on the radius that you have, essentially. Okay, pause the video, try a student problem. All right, so we're going to solve this one for y. So x squared plus y squared equals 9. So minus x squared. So y squared equals 9 minus x squared. So if I square root, I get plus or minus the square root of 9 minus x squared. Okay, well that means it's not a function, it's just a relation. So this is not possible. Okay, so the independent variable is x and the dependent variable is y. You just happen to get two y's for every x that you plug in, unfortunately. Okay, so let's talk about the function notation that we just did. So we can't write this one in f of x, but the ones you can actually use them. So it's basically the function machine. You put in something, you output something. So the x is the input, and the output is f of x, or otherwise known as the y value, right? Okay. So as you can see in my picture here, the x is my input, and the output is the f of x. Okay. All right. So I can write this equation in terms of y, or I can write in terms of f of x. Okay, so let's say I'm plugging in 30, right? So 30 is my x value. So f of 30 equals, what do we have here, 0.014, and then 30 squared, right? 30 squared. And then we have minus 0.24 times 30. And then we have plus 8.8. All right, so we're plugging in 30 into our function machine. So f of 30 equals 0.014. So that's 900 minus 0.24 times 30 plus 8.8. All right, so we did exponents first, right? Now we have to multiply. So 900 times 0.014, that gives me what, 12.6? So 12.6, and then 30 times 24 would be 720. Move the decimal, that'd be what, 7.2? So then plus 8.8. Okay, so we did exponents first, then we did multiply, and now we'll add. So we need 12.6, and we're going to add 8.8, but we're going to take away 7.2. So that's what, 14.2? Okay, so in function notation, it's f of 30, and in equation notation, it'd be y equals 14.2. So essentially, our coordinate is 30, comma 14.2 on the graph, right? So whether you have a coordinate or a function or an equation notation are all essentially equivalent. Okay. Well, what's important to understand is if for every input there's only one output if it's a function. And that is the end of part 2.